All right, everyone. Thank you for joining. My name is Jonathan. I'm with Flashbots, and today we're talking about how to efficiently sign encrypted transactions in FHE. So let me give you a bit of context first as to why would we even want to do that. You might be aware that we are working on something called MEV, which stands for maximal extractable value. It's known to be a problem on public blockchains. I'm not going to, give you like a full rundown on MEV. We don't have time for that. And I've got many talented colleagues who are here speaking today, which I encourage you to attend their talk or look up online afterwards if you want to learn everything you have to learn about MEV. The only thing we'll have to agree about is that MEV is a problem we can tackle. And if we want to tackle it properly and not to fall in this MEV trilemma that we've got here, we have got to inject privacy preserving methods in it to make it better. And of all privacy preserving methods, we'll particularly focus on FHE. So just like a one slide shortcut about what is FHE for those who don't know yet. So it's just this idea that instead of like encrypting something and not being able to do anything with the ciphertext, you retain the possibility to compute over what you've encrypted, right? So it means I encrypt something, I give it to you, I don't trust you, you can still do computation on it, give you back the result, for example. So it's great. It sounds magic. There's a few things to keep in mind is that there's a huge overhead when you're doing that, of course, so it's not free. You add noise, you have to manage this noise, so it's like, it tends to be expensive. So most of the time you want to be careful what you do with it, and especially like how you're doing it. So it's not as trivial as like I take an algorithm and I just like throw it into the FHE circuit. And we say circuit, by the way, if you hear me say circuit or program for FHE, same thing. And the idea is like we want to use this tool as like a first layer to maybe build a mini encrypted mempool in a way. So most of the issues we've seen with MEV stem from the fact that all transactions are visible in the traditional old school mempool. What if we encrypt them, but we want to retain the ability to compute over them? Okay, so we did that actually in a paper from this year's FC conference, if you want to look it up. And to summarize it in like one slide, we want to enable the ability for a searcher, so these actors that extract the MEV on the network, to backrun a user transaction. And what we mean by backrunning, it means that I'm able to, in a way, react based on like what I see in a user transaction and create my own transaction that I want to be executed right after the user transaction, which is why we call it backrunning. That's because of how the blockchain works, is that you have perfect certainty on like the state between these two transactions, because there's nothing changes between the execution of two transactions. So if you are trying to do something based on external events like the price on a centralized exchange, you know that at least whatever happens on chain is not going to change between the user's transaction and yours. Hence, you want to backrun. And the settings we had was relatively simple. So we assumed like a user transaction. User encrypts the transaction, sends it to the searcher in one way or another, encrypted mempool, direct RPC, whatever you want. And the searcher can run an FHE circuit that basically encodes what we call like a searching strategy that computes over the user's transaction, tries to see how it's going to impact the price on a Uniswap pool, for example, and generate its own backrunning transaction based on that to capture an arbitrage opportunity. Right, so the searcher now has an encrypted resulting transaction, right? That's the result of our FHE program. And it sends it to a builder. And in our setting, the builder is trusted. The builder can decrypt and has the job to basically package all that and put it in the block to land on chain. That's great. Or is it? What's missing here? Well, we've not talked about signing, right? So the FHE searcher is generating a transaction, which is basically like a raw transaction in a way, but it's not signed. So it's not going to land on chain, right? So, okay, the obvious thing you'd tell me would be, why is it hard to sign in FHE? Well, if you know your Ethereum, you know that we're using a combination of like keccak hashes and ECDSA to sign transactions. And these two things happen to be pretty cumbersome to handle in FHE. ECDSA is an elliptic curve-based signature scheme. It tends to be expensive to run in FHE. There's like an interesting article on the Zama blog that estimates that it takes like 1 to 2 days on a 60-core machine to crunch like an ECDSA. To be fair, that's the extreme setting. Like they try to do everything in the encrypted realm. They don't pre-compute anything. They do like all the heavy modular arithmetic over fields within the FHE circuit. So that's kind of like the low, the very high end of like what you can expect. But before you can even sign that, you need to hash your transaction, right? So you need to run keccak within the FHE circuit. And that's tricky as well. There's also a paper at this year's FC that showed that, you know, even if they try to really push it to the limit, they can basically bring down the runtime of a keccak from 2 hours 30 to 1 hour and a half on the single core machine. So you can make that faster, but it's still going to be not super great. Well, you could maybe just like try to sign the resulting ciphertext, right? The searcher generates this thing. It's just like this blob of data. It doesn't know what's in there, but it just like signs it into the builder. Maybe, but remember that if we want to eventually have a valid transaction, once the builder decrypts it, that's still not signed. So it needs a new interaction between the searcher and the builder to finally get this searcher's transaction. And that's potentially so. It adds latency. We don't like that in MEV, so not good. Also, like many other things that could break, pretty hard to do composability with that. And you require like further cryptographic guarantees to do that properly. So we're not happy with that, right? I hope that now we align on like what the issue is. But before we dive into the approach, we still need to go through like 2 methods that are going to be relevant to the rest of the presentation. One is account abstraction, right? 4437 account abstraction. You might have seen that before. The idea is to introduce like many things by basically changing the way user accounts are handled from like externally owned accounts to smart contract-based accounts. And you can do a few cool things. You can like delegate payment. We don't care about that in the setting. The interesting thing you can do in that thing is that you can change the way that transactions are validated. So you see like there's like a validate user op, like step 7 on the diagram, and that is custom. So you can do whatever you want to validate a transaction. You're not bound to keccak and ECDSA anymore. That's interesting. And all you have to do is to package your thing into this data structure called user operation, and then a new actor, a new role that we call the bundler, is going to make sure to send that to your smart contract wallet somehow. Right. Okay, so let's see what's in there. So this user operation thing has 2 stages that are relevant. 2 stages that you need to implement, 2 stages that you can customize to execute your transaction. One is the validation, which is the one we want to focus on this talk. So the idea with that, this one is that that's where you implement the logic of how do you make sure that this blob of data in the data structure that we call the user operation is valid, and that the smart contract wallet can use it to generate a transaction on your behalf. That's what you want to do with the validation. And then the execution is basically executing the logic of the DApp based on the validated structure. But if we want to zoom in on this validate user op function, that's where we're going to have our custom logic, right? So here, that's where we can start encoding non-ECDSA signatures, which is great if we want to get rid of ECDSA signatures in FHE. So it's like one building block we're pretty interested into, right? Flexibility. The bundler, so this new role, doesn't have to be a separate actor, to be fair, but just like think about it as a new role that's off-chain, could be like a separate mempool, like aggregating user operations. The one thing we want to know about this actor or this role is that it needs plain text access to these user operations, because it needs to then post them on chain, right? So that's really a critical part of the solution. It could be anyone, because these actors can be incentivized by getting a tip based on like what's in the user operation. But maybe that's a natural fit for a block builder to double up as like a bundler. And we'll see why that could be interesting later. The one thing I want you to remember from that is that they do need plain text access to the user operation. So just like keep that in mind as like another stepping stone in our solution. New concept. We've seen account abstraction. Account abstraction allows us to basically get flexibility on what we use to sign and to hash. So what do we want to hash with? Well, let's see. There is this concept called Chameleon hashes. If there's one thing that you might know about hashes, is that one property we want is collision resistance, right? So I inject like 2 different things in the hash. It should be super hard to get a collision, to get like the same digest from the hash function. Well, here we actually want collisions, right? But we want control collisions. So it means we want a way for 2 separate messages, different messages, we want a way to on demand generate the same hash, right? And that doesn't come for free, of course. We want to do that by introducing what we call a trapdoor. So think about it as like a private key. So if I know a private key, I can run like a different hash function that allows me to find the exact same result than I had before on a different message. And hence, I get a collision. Why is it useful in our case? Well, it means if I can do that, I know the hash beforehand. So even before I know the actual message that I want to sign, I know the hash. So I can sign this hash, even before knowing the message. And I can sign it with whatever signature scheme I want, ECDSA or whatever. The way it looks, so we've got this secret key, just like a randomly chosen field element. And that looks like a group generator. So like that's a discrete log assumption. We just generate a public key on that. This public key can be shared, can go in a smart contract, for example. And the only thing we do is that's the operation at the bottom that we're using to calculate the hash. So as you see, it relies on like the message, our public key, and a piece of randomness that we've just generated on the fly, right? And using like some simple like arithmetic in the exponent, we can just get a new value here that is the hash. Interestingly, we've not seen the magic in it yet. What's relevant for that is that we want to be able to generate these collisions. How do we do that? Well, if we observe that, we've got our first equation that we had before, and now imagine the same equation. We want the same hash, so this h value. We want it for a different m prime, and a different random value, r prime. If we observe that, they're both using the same generator, we can just equate these things, and that's the equation we need to solve. So at the end of the day, we basically, when we want to find a collision, we just want to run this equation, right? So that's basically the step that we want to compute in FHE to generate a hash, a collision in that case. So that's pretty cool, because like using this trapdoor-based approach, we've basically reduced the complexity of hashing from multiple rounds of keccak, multiple rounds of bitwise operations of a large state, to a handful of arithmetic operations. So that should be faster, hopefully. Let's put this all together in the methods. Okay, so remember our goal is to sign an encrypted transaction without relying on very expensive FHE signing operations. And now we've got the building blocks to split the signing process into an offline and an online phase. So offline, the signer can prepare the signature, right? Now we know how to know the hash of a future message in a way. So we can do this notion of like delayed binding of a message to a hash. We don't even know the message yet. It's going to come from the FHE, from the user actually. But we can still pre-compute a hash, and we can still pre-sign this hash even before starting the FHE bit. And the FHE bit just like ends up being like calculating this collision that we've seen before. So just to make it clear, what we do concretely is that offline, the searcher in clear text, so no FHE, picks a random number, computes the initial hash over a dummy piece of data, doesn't matter, signs it with whatever signing algorithm it wants, and keeps it somewhere, right, privately. Then online, when it receives the input from the user encrypted, it does like all the MEV magic that it wants to extract, and when it needs to sign, then it just has to inject the pre-computed values and calculate the collision as we've seen before. So that's what we need to sign a transaction in FHE in a way. Now, when we want to verify that on-chain, assume like our bundle has landed into the different mempool using the bundler. Well, the validate user opt function only has to recompute the hash, and we know it's kind of like trivial using the public key that we've stored maybe on the contract. And verify the signature on this contract, on this hash, sorry. So that's the two operations. We can even like think about it as like having different hashes. We can reuse the keccak of the envelope for the user operation if we want to skip like more signature verification and save some gas. But that's just details. But basically, that's the two steps you need to do. So to summarize that, offline, that doesn't look great, but that's all right. There's like more flashy colors on my version. But that's like green, red, and blue. Searcher picks a random number, pre-calculates a hash, signs it, and then when it comes online, just looks for the collision using the simple equation we've seen. Online, the user wallet checks the hash using the public key and then verifies the signature on this hash. And the way our builder comes into play, and I hinted before at the fact that the builder was a good fit to be a bundler, is that remember we still need to have plain text access to the user operation data structure. So once the searcher circuit has generated the hash using the Chameleon algorithm, it sends this bundle to our builder. And we're happy with the builder to trust it because it runs in a T. Like most of the builders these days happen to run in T. So we can kind of like trust them and give them secrets. That's like an okay assumption. So the builder can decrypt whatever it received and pack that into a user operation that it sends to the user's smart contract wallet. So basically, we've closed the loop and we've solved our requirements. How does that look concretely? Well, this is like still a very early prototype, but I just wanted to give you an idea of like how it could look like. It's using insecure values, so don't assume that that's going to be the final numbers for this kind of approaches. But basically, the overhead in terms of like the smart contract wallet should be around 14 to 16K gas. It's basically dominated by like doing an EC recover to validate, to verify the signature, and modular exponentiations to calculate the Chameleon hash. So it's not too bad. And on the FHE side, for a relatively unsafe and low modulus, we can get to 1 million bootstrap operations, which is what is really like the juice of FHE and where the overhead comes from. And it runs in a couple of seconds on the laptop. So going to higher secure modular, we'll have to go for larger servers, of course, but there's a good chance that it still remain manageable, which is great. One thing that's not too great right now is like we're currently mixing different security assumptions. FHE is like post-quantum. We've injected like discrete log assumptions in there. So it might be great to have like everything post-quantum down the line. But that's also a good use, as we've seen, for the synergy between T's and FHE. One thing that I really like to remind every time is that all of these privacy enhancing methods should not be thought of as like a silver bullet. Most of the time you want a combination of them to operate together, and that's like a very good example here. If that's inspiring, we happen to have many more of these problems online. That's new. We've just shared our research problems database, and you're more than welcome to check it and come to chat with us about it. We're going to be there all week. Another info from our sponsor is that we are hiring. And we are looking for different roles, both in product and research. And we happen to have like our amazing recruiters at FCC this week. So you can come and speak to us. You can come to speak to our recruiters. Or you can just like look these information online if you want to. Thank you very much for bearing with me.
Have you looked into any distributed key scenarios?
So that'd be compatible with distributed keys. I guess the where it could come into play would be that instead of like having you don't have the slides anymore, but like remember there was like a builder with a secret key in there. That would be the obvious place where to inject distributed keys. You could still have them in TEs, but what you'd have is like you'd have this threshold decryption of like FHE ciphertext with the shares each maintained in like different TEs, for example. So it's totally complementary. Yeah. Thanks so much.